Hello dear students, this is Devang Shah from LG Institute of Engineering and Technology. We have been learning the subject basic electrical engineering. We were studying about network theorems, so basics of network, then Thevenin theorem, Norton theorem, superposition theorem. After that, we need to learn about the nodal analysis and mesh analysis. Now, these are nothing but the extended version of Kirchhoff current law and Kirchhoff voltage law, right? Now, in which condition you can apply Kirchhoff current law and Kirchhoff voltage law? When there is a big network, very big circuit, and in this big circuit, if you want to find voltage drop across particular resistance or current which is passing through a particular resistance, that again you can apply this particular method and you can find voltage and current according to that. So this is nothing but one of the method, one of the way of solving a circuit diagram, right? So if we first talk about the nodal analysis, now as I say, it is an extended version of Kirchhoff current law, where ultimately you have to find the node, right? So this is a generalized circuit you can see here, right, where your first job is to identify nodes. Here you can see from this particular circuit, your first job is to identify the nodes, right, where you can see here, as per the definition of node, three or more than three branches must be connected at a point where it is considered as a node. So in this particular circuit, there are three nodes as node A, node B, and finally node C. But here the node C is connected to ground. So you have to always take the consideration of node C. The voltage at node C must be equal to 0. Right? Number of nodes, then n minus 1 number of equations. Right? Now, once you apply this analysis, you have to consider you yourself as a node, right? Let's say if I consider a node A, that means you yourself as a node A, where you have to apply the extended version of KCL, or you have to apply the KCL. Now you already know at particular node some currents are incoming and some currents are outgoing, right? So ultimately you have to find the sum of incoming current towards the node is equal to sum of outgoing current from the node. Now, within the same formula, we can apply a nodal analysis at node A. So, once you consider yourself as a node A, right? So, you are looking, or you are sitting at the node A, and from there you are looking. The total 6 branches are connected in this circuit. You are as a voltage VA. So, you are at a supreme condition voltage VA, and you can check here your first branch as VA, right, and on another side V1 is connected at this particular branch. So, if you are looking and you can see the positive terminal, that means you have to make it a subtract from the node voltage. So, VA minus V1 minus VC. Now, why minus VC? Because it is the another end, you have to also take the difference of that particular voltage. So, here your as a first branch number 1 as a first term, and all these terms are in form of the current terms, because ultimately here we are applying KCL, right. So, your first term from the first branch is VA minus V1 minus VC divided by resistance R1. So, ultimately as per the Ohm's law, this is V is equal to I into R, right. So, here we have taken as a form of current I is equal to V by R, right. So, your first term is nothing but VA minus V1 minus VC divided by R1, that is represented as your current I1. Now, here you forget about the current directions, right. Why? Because the circuit is very big, where some currents are coming and some currents are outgoing from the node. So, in this condition you have to go for a standard way of analysis, and that particular analysis we define as a nodal analysis, right. So, here we first take the node and then we do the analysis, and all the terms we define here in equation, all are the current terms, right. Same way, if you look for a branch number 2, your term is VA plus V2 minus VC divided by R2, right. Now, you can see the branch number 3, where I1 current is coming to you, right. So, ultimately that you have to subtract from the equation. So, it is a minus I1, that is your branch number 3. Now, branch number 4, you can observe here I2, which is coming from the node. So, you have to consider as a positive. So, plus I2, then plus you can see the branch number 5, where only R3 is connected, right. So, another end, there is only VC. So your term is like VA minus VC divided by R3. And if you observe the branch number 6, where the other side you have a node B. So this would be VA minus VB divided by R4, and that is equal to 0. So that the complete equation you can observe again branch wise one by one. So you can find here the complete equation, and that equation is nothing but the extended version of Kirchhoff current law that we represent as a nodal analysis, right? Since in this circuit you can see VC is equal to 0. So in this particular equation, if you put VC is equal to 0, then again the same circuitry where you can redefine your equation, where you can take V2 is equal to 0. So here VA minus V1 divided by R1 plus VA plus V2 divided by R2 minus I1 plus I2 plus VA divided by R3 plus VA minus VB divided by R4 is equal to 0. That's how you can apply nodal analysis. Now this is at the node A. Now same way, same formula you can apply at node B, and again once you consider as a node B, so that means you are as a VB, right? And again you have to figure it out how many branches are connected at this particular node. So if there are n number of branches, there are n number of current terms you will find in this nodal analysis. So you can see here, once you apply nodal analysis at node B, you can find the complete equation, where again as you sort it out as per our previous discussion, branch 1, 2, 3, 4, 5 and 6, you will find this particular equation where VB minus V4 minus VC divided by R6 plus VB plus V3 minus VC divided by R5 minus I4 plus I5 plus VB minus VC divided by R7 plus VB minus VC divided by R4 is equal to 0. Again, all these 6 terms you can check here, all the terms are the current terms where VC is equal to 0. So you can here redefine the complete equation here in that form, where you make it VC is equal to 0, you can find this particular equation, and all terms are the current terms, right? Now the same analysis we can apply for a one particular circuit. Let's say we take one example where you have to find the value of the branch currents for the network shown in figure using the nodal analysis, right? Where your first job is to identify nodes. So how many nodes from this circuit? You can easily see at one particular node there are 3 branches or more than 3 branches are connected. That means here there are 3 nodes, and one node is permanently connected to ground. So voltage at that particular node you can consider as a 0, right? So here again we have a total 3 nodes, A, B and C node we consider as a ground. So from this here my job is to find node voltage is VA and VB, right? Same applying the nodal analysis at node A, I'll find my first equation as a node A, where VA minus 20 divided by 1. So the same formula we can just discussed earlier, plus VA minus VB divided by 0.5 plus VA divided by 1 is equal to 0. Now this is the nodal analysis at node A. Same way you can apply nodal analysis at node B, and you can find the equation. So here once you apply nodal analysis as node A and node B, simultaneously you can find there are 2 equations. One equation is 2 VA minus VB is equal to 10. Another equation is 2 VA minus 5 into 3.5 into VB is equal to minus 20. Once you apply here elimination method, and from elimination method you can be able to find VA is equal to 11 volt and VB is equal to 12 volt, right? Now the next important part is that you have to find the branch currents, each branch currents from this particular circuit. So you will find I1 current, which is passing from 20 volt source up to VA. Why? Because VA is 11 volt and VB is equal to 12 volt, right? So current is always follow the path from higher potential to a lower potential, right? So from this you can be able to find all currents I1, I2, I3, I4 and I5. So let's find the current I1, that is equal to 20 minus VA divided by 1 ohm resistance. So that is 20 minus 11 divided by 1, that is equal to 9 ampere, right? By that way you can find, so you can find all I1 to I5 currents, right? Now if you want to verify in real case you have applied KCL or not, So you have to find from node A and node B, some currents are entering and some currents are outgoing. So that summation must be equal to the algebraic sum of all this entering current and outgoing current must be equal to 0. That you can verify from this circuit, and you can go through this nodal analysis. Right now, our next important term, which is called mesh analysis, this is nothing but the extended version of Kirchhoff voltage law, where all the terms you consider as a voltage, right? So now for that, what is important here? Important is that your job is to identify the loops. Loops in another sense is a closed path, right? So in our in our nodal analysis, we have identified nodes, but in a mesh analysis, we have to identify loops. So here in this particular circuit, you can find there are total 3 loops. So if n number of loops, then n number of equations, right? So current which is passing through particular resistance, let's say you consider as a in loop number 1 R1, where 2 currents are passing, I1 and I3, right? So let us say if you consider as a loop number 1, that means you behave as a current I1. If you are considering loop number 2, that means you are as a I2, as a current I2. And if you are considering loop 3, that means you behave yourself as a current I3, right? So from this analysis you can find let us say loop number 1, and that particular is AB DA, that particular loop where your journey starts from resistance R1 as you yourself consider as I1, right? So now you are passing through R1. So which current is opposing you? I3 current is opposing you, right? So R1 in bracket I1 minus I3, this is my one term. So now this term is R into I. So the term is defined as a voltage term, right? Same way, once you go to point number B, and then you have to go now from B to D. That means you are passing through R2, right? So you are as a current I1, and which current is opposing to you? I2. So your second term is plus R2 in bracket I1 minus I2, right? And once you finish the loop, you can go from D to A. You can see here that V1, right? The first sign of V1 as a battery, you face as a minus. So you put it straight away, minus V1 is equal to 0. So ultimately, this term is nothing but Kirchhoff voltage law, right? Once you apply 10 volt, the 10 volt must be drop across the loop, right? This is the consideration. Now same consideration if you can apply for a loop number 2, you can see here B, C, D, A. This is a loop where you apply here R3, where 2 currents are passing, and you consider now yourself as a current I2. So R3 in bracket I2 minus I3, because I3 current is opposing once you are moving from R2, right? Same way plus V2, because the first sign you can see here plus V2 here, and plus R2 in bracket I2 minus I1 is equal to 0. This is about the loop number 2. Same way you can apply for a loop number 3, which is the above loop is A, C, B and A, right? Where across R4 you are passing like I3 current is passing through R4 into I3 plus R3 in bracket I3 minus I2, because I2 is opposing, it's in opposite direction. Same way plus R1 in bracket I3 minus R1 is equal to 0. Now this this analysis, this derivation of equation is based on Kirchhoff voltage law, because each term is representing as a voltage. So by this way you can analyze any circuit using the mesh analysis. Now one of the example we can see here, straight away same circuit we have just put the values of resistance, voltage source. So once you apply loop number, once you apply the here mesh analysis from the loop number 1, you can be able to find the 8 ohm resistance, that is where 2 currents are passing. If you consider as a loop 1, that means you yourself as I1 and I3 current is opposing. So you can see here 8 in bracket I1 minus I3 plus 20, where you are flowing through 20. I mean I1 current is flowing through 20 and I2 current is in opposite direction. So plus 20 in bracket I1 minus I2 minus 10, right? The first sign is a minus 10 is equal to 0. So that's what the loop number 1. So now same analysis you can apply for loop number 2 and loop number 3. You can be able to find the complete equation in that form. You can see from equation number 1, 2 and 3, you will find the complete this equation. Now in this particular equation, if you go for a elimination method, it would be very typical, so very tough. So what we choose the easiest method called a Cramer's rule in matrix. So once you solve this complete three equations using the matrix, you can define a matrix here. You find the delta from the matrix. You will find the value of delta is 2 1 1 1 0. Then you replace the voltage by first column, you will find delta 1 or D1. So from this you can be able to find the I1 current, which is delta 1 divided by delta, or D1 divided by D, and that is equal to 1.132 ampere. Same formula you can go for replacing the second column by the voltage. You will find D2 I2, which is 0.711 ampere, and same way you can find the current I3 by finding delta 3 and by divided by delta, right. So throughout this particular operation you can be able to find all the loop currents I1, I2 and I3, right. So that's how you can solve any network by these various methods of network. Thank you very much, dear students. If you find any difficulty, please write in a comment box.